Alright, ladies and gentlemen, so in this video we're going to start diving on into 2.2 of our pre-calc talk, which is about polynomial functions of some higher degrees. So the goals of this particular lesson are going to be to look into how to use what we call the leading coefficient test to determine n behaviors of graphs. And let me take a quick moment on this for our leading coefficients. This leading coefficient can be super important as we dive deeper into calculus. So at least we have some more ideas as where the limits are going to be approaching, and then how at some point as well too what the derivatives are going to look like and what the second derivatives are going to tell us about the graphs itself. We're also going to look into how to use zeros of polynomial functions to sketch graphs, and we're going to go ahead and dive a little bit into what we call the intermediate value theorem. That's going to help us locate where the zeros of the solutions of a polynomial function actually end up being. So let's open up the discussion here, guys. What you see on the screen right now is some characteristics. The characteristics of the graphs of polynomial functions. There's two key things that we need to take into account. Number one, the graph of a polynomial function is continuous. So with quick recap, we're going to dive deep into continuity. But if you remember correctly, what it means to be continuous, basically you can take your pencil over the entire graph and not have to lift it on up. There is no breaks, there's no gaps, anything like that. So it has to be a continuous function. The second key feature is a polynomial function only has smooth, rounded curves and turns as it's making some transitions. They're going concave up to concave down, or any of the case may be. So what you see down here, guys, is an example of our absolute value function, which would not be a polynomial. So this is exactly what we're talking about. This corner right here is going to show that it is not a smoother or rounded curve, so that will not show a polynomial function there. So we can see a lot about what the function itself is by the curves or turns of the graph itself. So let's dive into just a quick, it's a brief tip I have for you. It's kind of more just a food for thought. So let's think first that we have a function. We're going to call it f of x. We're going to say that equals x to the n power, okay? So just remember, if n is even, so this is our exponent, it is an even degree, then the graph is symmetric with respect to what? Well, if you think about what we had talked about for even and odd functions already, and hopefully you remember that when that is an even exponent, or the degree is even, we are going to see symmetry about the y-axis. Now, if n is odd, then the graph has symmetry with respect to the, well, if you remember, there was a significance. We kind of used a little trick to help us remember. Odd, O for origin, right? So can kind of keep that in mind, O for origin. If n is odd, or if it's an odd degree, then it's going to have symmetry to the origin itself. All right, so let's dive on into the real first part of our goal, is to look into the leading coefficient test. Again, what is it for? Why do we use it? Well, we really focus on using it as a way to say the end behavior. What does end behavior even mean? Basically, is the end arrows of a function going up or down? Is it increasing or is it decreasing? Is it going to positive infinity or negative infinity, right? And it all can be dependent based on what the degree and the sign of the leading coefficient is for our leading coefficients. So let's say, for instance, that we have a polynomial function as we see up here. Pretty basic, right? Nothing too crazy going along with it. Well, how can this tell us about the end behavior? Well, it's because we know kind of what the parent function does, right? We know something about what the parent function looks like. It can kind of help us say what the right and left hand or the end behaviors of a graph are going to be. So we have four scenarios. The four scenarios are based upon the two different scenarios for odd and even functions. So if the degree, the highest exponent, is odd and the leading coefficient is positive, then we're going to fall and then rise from left to right. If it is odd and it is a negative sign of that leading coefficient, then we're going to rise and then fall. It's going to be the opposite approach to it. And as you continue to go through these, start thinking about what these graphs are looking like. I think you're going to start understanding that once you look at a quadratic, you look at a cubic, you're going to see, oh, well, duh, that kind of makes sense. As you have an even function with a positive leading coefficient, you're going to rise and then rise again, right? You're going to rise and then rise again. And then lastly, when you have even and it's a less than 0, or it's a negative value for that leading coefficient, then you're going to fall and fall. I mean, the easiest thing I can say for this third row that's in here, guys, is just think about what happens for a simple quadratic parabola, right? Both those arrows for x squared, right? If y equals x squared, both those arrows go up. They're rising in both of those scenarios. But immediately when I put negative x squared, everything's facing downwards. So that's exactly what you're trying to show there. So let's look at an example how we can utilize this to our advantage here. So it says describe the right and left hand behaviors. You may also just see it written as the end behaviors. So we analyze first and foremost the leading coefficient. The leading coefficient here is negative. That leading coefficient is negative. So right on off the bat, I'm looking leading coefficient negative, leading coefficient negative. Then my next thing is to understand, well, what's happening to my degree? Well, my degree is odd because the highest exponent is 3. 3 is an odd number, right? So now I look for where the leading coefficient is negative and the degree is odd. What that tells me is that the left-hand behavior is going to rise, the right-hand behavior is going to fall, okay? Let's keep moving on. Give these two a shot on your own. See what you can come on up with using our chart and what we just found out about end behaviors. Find out what that leading coefficient is, find out what the degree is, and see if you can figure out what each of these two functions are up to. On to the next one.